Today, I would like to talk about performance testing. Well, I call this presentation performance analysis, but the majority of what I'm going to talk about will be about performance testing. And this is actually what I have been doing for a couple of years, since 2007. And just a few lines about me. And I have some background in Java development, but I only worked in that area for 1 year, and then I switched to software testing. And since 2007, I have been working as a performance tester at Dear to Every. So on such occasions, I usually start talking about, I want to motivate people to do or to think about performance a lot more than it's actually done before. Because even though over the years I have been doing this job, I have a feeling that performance has strengthened, or the focus on performance has strengthened, but despite that, there are a lot of issues still, because if you look at reality and especially, my very narrow world, I don't know how it works outside of my bubble, but at least my impression is that performance is done always at the very last moment before software product is rolled out to production. So it's unfortunately too late to make any changes. So that's my complaint about the current situation. As I said, I don't have any tangible evidence at my hand, so I can't say anything about how it works elsewhere, but this is at least my impression, my experience. So just to remind you of why performance is important, I have selected two examples. The first one comes from 2021. It's actually the first attempt to do national census in an electronic way in my country, and it was, in the end, it was a success, but there were a lot of obstacles at the beginning to overcome. When the system was launched, a couple of hours later, the system was unusable, there were performance issues, and what I have learned from open sources, the main problem was this predictive address search. So how it worked, I drew this simple diagram to illustrate this issue. So every single attempt, so every time you typed a letter in this field, there was a request sent to the database, and a list of addresses was returned. And as a result, it turned out that the load created by end users was so high that it overwhelmed the database. Supposedly, there was performance testing done on this system, but unfortunately, at least what I think might have been the issue was that the strategy, or the way how the artificial load was simulated with load generators, wasn't done properly, especially on this side. The second example is about another web application which was intended to register participants, or perhaps not participants, but everyone who was interested in vaccination against COVID-19. And it was actually my age category, which was open a couple of minutes after the midnight back at the day, and it crashed. So there were two phases, if some of you might have remembered. The first was registering yourself, then you had to wait for an SMS, and the second phase couldn't be completed because no SMS actually came. I have no information about why or what exactly was wrong in the system, but reality was that it again, crashed in a similar way, or perhaps, well, the user experience was bad due to this inability to use the system or to complete the registration flow. So this is motivation, and well, as I said, every single time I talk about performance, I try to persuade people about the importance why performance should be taken into consideration and should be thought as an important or crucial aspect of every software development life cycle. Now back to the agenda. I'm going to talk about two topics. The first one is about performance evaluation times, what we have, what we can do, and then I will turn to an example which I have developed, or it will show you how my daily job actually looks like. Well, if we should define what performance is, at least what I understand as performance, I look at the system from a holistic point of view. So I see several layers that compose, that are part of any software system, and we should look at every single layer or monitor every single layer, because if any performance problem comes up, it might be everywhere. So not only the UI, not only the database, but also the system layer, the operating system itself. If you look at any bug databases, you can find a lot of issues, even related to Linux operating system, Unix, Windows. So it's not rare. And objectives are clear. Improving user experience, this is what we are trying to do when evaluating the system for performance, when fixing performance-related problems, and of course reducing costs, because if we increase throughput, if we reduce latencies, response times, we can use hardware with less capacity, and nowadays with cloud services we can save a lot of money. This is a very simple diagram showing how the software stack looks like on a single server. So this is what you should imagine behind any system if you are going to analyze a software product running on one machine. So there is a lot of stuff behind or under the hood, and especially operating system shouldn't be left out, and should be really considered as one possibility where problems might be found. Typical activities, there are plenty of them, and I have chosen only this list. I'm not going to go into details, but just for information, in my case, these are the three activities I'm dealing on a daily basis. The other ones are very rare in my case, and for example, analysis of production problems I have done just once or two times overall. So these three activities, are what I'm doing. Now, let's have a look at what types of performance evaluations we have. We have three different types, or we can categorize them into three groups. First, observational. I'm going to look at it more closely when going through a case or example I have put together. Analytical modeling might be something not anyone of you is familiar with. And experimental. Experimental is my main focus, so it can be called benchmarking. Now, let's have a look at each of these categories. First, observational. The principle is simple. So, application or operating system exposes some data, and we can use the data to evaluate the performance, the behavior of that component, product, software system. And we can use counters. For example, in proc directory on Linux operating system, you can find a lot of counters. Counters are used to calculate statistics, and then a selected list of statistics is metrics. Then profilers are important tools. I'm going to show you two types of profilers, and then tracers. All of these sources are valuable when you need to analyze performance data in a kind of observational way. But cautious has to be taken, because if you set a lot of probes, if you set a lot of if you feed a lot of observational data, then it might happen that you will affect the way how the system works, or you will create substantial overhead that will skew results, especially when you run your benchmarks. Analytical modeling theory is based on mathematical models. There is one theory called queuing theory, which is absolutely crucial in evaluating performance, and there's a lot of stuff you need to learn if you want to excel at this field. So it's about math, probability, statistics. The idea is that anything that contains queues can be modeled with this theory. So even if you go to a shopping mall, there are a lot of queues, and you can apply the principles and the theory behind this easily, even when you analyze how the situation in a shopping mall, evolves. A very simple queue is depicted on this picture. So you have one service center. You can imagine it as a server, and then you have a queue. Service center can be anything. For example, CPU. CPU has its own queue. There are incoming requests, queuing if the service is not able to handle the rate, arrival rate. And there are different methods how you can model arrival process, service time distribution. So you should study how it actually looks before you choose the right model. And this is MD1. This is Kendall notation. It means that arrival rate is stochastic process. It follows Poisson distribution. And then service time is constant, so it means that the service replies or processes your request in the same way, in the same amount of time. And the number of services is only one. So just for your information, if you find or come across this queuing theory term, then you will remember that there's a lot of behind this, and you can apply it to any system that contains queuing and queues. Now let's have a look at experimental benchmarking, and this is my area. And benchmarking can be divided into two groups: micro benchmarking and macro benchmarking, and I'm focusing on macro benchmarking. And there are some notes that distinguish these two categories. Micro benchmark have the advantage that the scope is narrow. So you do not have a complex system in front of you. You don't need to study it for a long time to understand what it actually does and all these nitty-gritty details of it. But on the other hand, micro-benchmarks can be easily misled, or you can mislead somebody when you do micro-benchmark without knowing what you actually do, because if you go deeper and deeper and your scale reduces to microseconds, nanoseconds, then you should be very careful what you do in your micro-benchmark. Otherwise, you will measure completely different than what you intended to do. An example of micro-benchmark, iPerf tool that tests the throughput between 2 points. You have a client, you have a server, and you test the throughput of this connection. And it's a very simple tool, so it throws as many TCP requests as possible from the client side to the server side. The server replies, and then you measure the runtime, and based on it, you calculate the throughput. This is an interesting table because people are very, don't understand, those load times, or you can hardly, or we can hardly imagine what is behind those very low times. And this table is actually a kind of conversion between the latency. You have a few examples, one CPU cycle, tens of nanoseconds, then when you calculate it to 1 second and compare the other activities that go on around computing, then you can have comparison. And when you compare, for example, main memory access, so it's 1 second against 6 minutes, and it's a huge difference when you read your data from cache than from the main memory. And if you have an application that is memory intensive and you read a lot of data or write the data, then of course the time will be affected because you have plenty of operations to complete. So this is the reason why nowadays the talk is about reducing access to the main memory and using or designing data structures, algorithms in a way that you read data from your caches instead of the main memory. Now let's start with the web application. So as a performance tester, I have this assignment, for example. It's deliberately designed to be very simple. It's a web application that has only 2 services. One is for storing, or the service through which you can store your measurements. The other one is calculating statistics, so it takes all the measurements you save into a file in this case, and then calculate statistics on these 3. Now, system diagram showing the situation. So the web application is running on a virtual machine on the Sun HTTP server. Below that is OpenJDK. So yeah, a very simple one. Use case diagram, pretty simple. This is graph called behavior diagram, and this graph is pretty useful when you design your workload model. And it will show the activities that will be part of the performance test, the workload, and then probabilities. So how likely is it for you to transfer from this activity to another one? It's Markov diagram, yeah. So we have the situation that these two services are going to be used in that ratio of traffic distribution. Then we have these requirements. So unfortunately, this is a very ideal case, and reality, you have difficulty getting any tangible requirements from your clients. It's a long haul usually, long haul between your client, between you to get as many requirements from them, because in most cases the people have no idea about what the system should do, and they have no idea about how fast the operations should complete. So it's a long talk. Sometimes you fail because the client simply doesn't know what he needs. But in this case, let's assume we have these requirements, and now what we are going to do is to create a script, or we need to simulate this load, and we have one option to simulate it with people, which is impractical. Another one is using a tool. I use different load generators, for example, JMeter. JMeter is my primary tool. Then I use K6 load runner. And depending on the situation, I choose one of them. Now, I have completed a couple of performance tests before this meeting, so I have some data, and this graph shows response times of the first service at measurements, and this is histogram, and it's especially useful because it shows you the distribution of the response times. Be very hesitant when somebody asks you to give the average, or forget about averages, about mean. Average is misleading metric, and instead of using averages, you should use higher percentiles, and even better is to use histograms like this, so you can see exactly which of the bucket contains most of the values, most of the response times. This is modus from statistics, and you can see there are plenty of outliers here, and the aim of performance analysis is to find the reason, the cause of those outliers, because if you get rid of these outliers, you have this graph, and this and the performance will boost if you can remove those outliers, if you manage to find the root cause. I have very little time left, but just you don't see that graph. Oh, here we go. This graph is called flame graph, and you can create it, I created this graph using a BPF tool called Profile, and BPF is very promising. This technology has been around for a while, but this technology allows you to get very detailed data about your kernel behavior. So you can dive deeper into internals of your kernel, and you can find not only the user aspect of because you have several profilers. You might note some of them: JMC, Java Mission Control. You have Visual VM, but those profilers focus only on the user part. You can't go deeper to the system level. But if you use a BPF tool like this, you can see these stacks from here down up to the top, and those stacks, those frames indicate how much time was spent on calling those system calls, because in some situations, system calls are the root cause of your performance problem, so you shouldn't leave them out from your analysis. How many minutes? 1 minute. Okay. And this is the graph from the second service. So my strategy was to benchmark each of those services separately to find out their limits, to find out potential performance problems. And then at the very end, what I did was to combine those services together, following the workload profile and getting these performance results, which are kind of interesting when you compare this response time graph with the graphs you saw before, because there's a kind of increasing line, and this is something worth analyzing further. And with that, I will wrap it up, and thank you for your attention.
We have time for one question.
I got one. You mentioned that it is difficult to get requirements from your customers.
Yeah.
So if it happens that you have no requirements, do you guess, or is there some golden standard?
Yeah, I do my best. I approach to this assignment in a way that I will set up a scalability test. So I first learn about what the system does, what the use cases are, and then I will simulate the traffic or the workload as realistically as I can with the time restraint. If I have only a couple of days, I need to take some trade-offs. So after I model this workload, then I implement performance tests and I use scalability tests. So I will gradually ramp up the load and find any potential performance limits. So I watch the response times trend, watch throughput, and at the moment when I see the first sign of performance degradation, I will report it and say, is it the load that is acceptable for you, or are you going to do more investigation into this issue and find the root cause? So yeah, this is the only way what I can do as a performance tester. I report this problem or potential problem because it might turn out that the management is absolutely fine with the results. But yeah, this is what I do without having any requirements available.
Okay. Mm-hmm. Thank you, Tomáš.
Pleasure.